Review of deepfake detection techniques. Abstract deepfake videos are AI-generated videos that look real but are fake. Deepfake videos are generally created by face-swapping techniques. It started as fun, but like any technology, it is being misused. In the beginning, these videos could be identified by human eyes. But due to the development of machine learning, it became easier to create deepfake videos. It has almost become indistinguishable from real videos. Deepfake videos are usually created by using GANs, Generative Adversarial Network, and other deep learning technologies. The danger of this is that technology can be used to make people believe something is real when it is not. Smartphone desktop applications like FaceApp and Fake App are built on this process. These videos can affect a person's integrity. So identifying and categorizing these videos has become a necessity. This paper evaluate methods of deepfake detection and discuss how they can be combined or modified to get more accurate results. Hopefully, we will be able to make the internet a safer place. Index terms: detection, classification, deepfake video, generative adversarial network, artificial neural network, machine learning. Introduction. A growing disquiet has settled around the emerging deepfake that make it possible to create evidence of scenes that has never ever happened. Celebrities and politicians are the ones who are considerably affected by this. Deepfake can optimally stitch anyone into a video or photo that they never have actually knowledge with. Nowadays, since technologies are elevating widely, the systems can synthesize images and videos more quickly. A creator would first train a neural network on many hours of real video footage to give it a realistic understanding of what he or she looks like on many angles or lighting in order to create a deepfake video of someone. Then they would combine the trained network into graphics techniques to superimpose a copy of person into different one. AI-generated synthetic media, which is also known as deepfakes, of course have many positive sides. Deepfakes enables clear benefits in areas such as education, accessibility, film production, criminal forensics, and artistic expression. It can accelerate the artistic quest into equity. Creative use of synthetic voice and video can enhance overall success and learning outcomes with scale and limited expenditure. Deepfakes can democratize VFX technology as a strong tool for independent storytellers. It could give individuals new tools for self-expression and amalgamation in online world. Deepfakes also has disadvantages which affects different groups of our society. It is being used to revenge porn, to defame certain celebrities, creating fake news and propaganda, etc. As soon as these fake videos goes viral, people believe initially and keep on sharing with others, makes the targeted person embarrassed watching this fake stuff. Until or unless an official statement of targeted one not comes, many keep on believing this stuff, making their life difficult and are followed attacked by the society in platforms like Facebook, Twitter via Instagram. 2. Discussion. Different types of deepfake detection methods are available today, and each method has its own advantages and disadvantages. This paper tries to evaluate such methods from different papers and points out how these methods can be combined and modified in a new project in order to get more accurate results. In the paper 1, Deepfake Video Detection Using Recurrent Neural Network, David Guerra and Edward J. Delp propose a temporal-aware pipeline to automatically detect deepfake videos. In order to detect deepfake videos, firstly we need to have a clear knowledge of how it is created, which helps us to understand the weak points of deepfake generation, so that by exploiting those weak points, deepfake detection can be done. In the approach discussed in this paper, frame-level scene inconsistency is the first feature that is exploited. If the encoder is not aware of the skin or other scene information, there will be boundary effects due to a scene fusion between the new face and the rest of the frame, which is another weak point. The third major weakness that is exploited here is the source of multiple anomalies and leads to a flickering phenomenon in the face region. This flickering is common to most of the fake videos. Even though this is hard to find with our naked eye, it can be easily captured by a pixel-level CNN feature extraction. Dataset used here contains 300 videos from the HOHA dataset. Pre-processing steps are clearly described in this paper. Here the proposed system is composed of a convolution LSTM structure for processing frame sequences. CNN for frame feature extraction and LSTM for temporal sequence analysis are the two essential components in a convolutional LSTM. For an unseen test sequence, set of features for each frame are generated by CNN. After that, features of multiple consecutive frames are concatenated and pass them to the LSTM for analysis, which finally produces an estimated likelihood of the sequence being either a deepfake or non-manipulated video. With less than 2 seconds, the system could accurately predict if the fragment being analyzed comes from a deepfake video or not with an accuracy greater than 97%. In the paper, Two Effective and Fast Deepfake Detection Method based on Har Wavelet Transform by Mohammad Akramianis and Taha Mohammad Hassan describes another method to detect deepfake videos by Har Wavelet Transform. The method described here take the advantage of the fact that during deepfake video generation, deepfake algorithm could only generate fake faces with specific size and resolution. In order to match and fit the arrangement of the source's face on original videos, a further blur function must be added to the synthesized faces. This transformation causes exclusive blur inconsistency between the generated face and its background outcome deepfake videos. The method detects such inconsistency by comparing the blurred synthesized areas ROI and the surrounding context with a dedicated Har Wavelet Transform function. The two main advantage of this Har Wavelet Transform function is that it first distinguishes different kinds of edges and the retrieves sharpness from the blurred image. It is very effective and fast since the uniform background of the faces in the images will have no effect and it does not need to reconstruct the blur matrix function. To estimate the blur extent, two methods such as direct and indirect can be used. Direct method can measure the blur function extent by testing some distinctive features in an image, e.g., edge feature. The indirect method depends on the blur reconstruction function when the H matrix is unknown. H matrix is blur's estimation and blur identification. Dirac structure, step structure, and roof structure are the different types of edges present in an image. A blur extends is identified by taking the sharpness of roof structure and G-step structure into account. The sharpness of the edge is indicated by the parameter 0/2, if is larger means the edge is sharper. By comparing the blur extent of the ROI with the blur extent of the rest of the image, we can determine if the images, frames of video, have tampered or not. UAD dataset, which contains 49 unmanipulated and 49 manipulated videos, is used here. Videos are divided into frames and from each frame, the face region is extracted and deepfake detection algorithm using Har Wavelet Transform is applied. This algorithm is clearly described in this paper. This proposed model contains an accuracy of 90.5%. In the paper 3, OC Fake Detect, Classifying Deepfakes Using One-Class Variational Autoencoder by Hassam Khalid and Simon S. Wu, the proposed model needs only real images for training. As new methods for deepfake video creation are increasing today due to technology advancement, for a model to detect such videos, datasets containing fake videos are very scarce for training. It affects the model's accuracy. But in the model proposed in this paper needs only real videos for training so that it can overcome data scarcity limitation. Face Forensic ++ is the dataset used here. It contains real images and 5 sets of fake images: Face Swap dataset, FACE2 FACE dataset, F2F, Deepfake dataset, DF, Neural Textures dataset, NT, Deepfake Detection dataset, DFD. After collecting the video datasets, they are converted into frames and face detection and alignment is done using MTCNN. One-class variational encoder is used here. It consists of an encoder and a decoder. At the encoder side, image is given as input, and scaling is done using convolutional layer, and mean and variance is calculated and the result is given as input into decoder, and the RMSE value is calculated, which is low for real image and high for fake images. Two methods are discussed in this paper, IJERT1 and IJERT2. In IJERT1, from input and output image itself, reconstruction score is computed directly, and in a fake DEC 2 contains additional encoder structure which computes reconstruction score from input and output latent information. Even though it has 97.5% accuracy, better performance is only on NT and DFD datasets. In the paper for deepfake source detection via interpreting residuals with biological signals, Umur Abersiftsai, Ilka Demir, and Vijayan presented a deepfake source detection technique via interpreting residuals with biological signals. To their knowledge, it is the first method to apply biological signals for the task of deepfake source detection. In addition to this, they had experimentally validated this method through various ablation studies. Their experiments had achieved 93.39% accuracy on face forensics ++ dataset on source detection from 4 deepfake generators and real videos. Other than this, they had demonstrated the adaptability of the approach to new generative models, keeping the accuracy unchanged. After studying biological signal analysis on deepfake videos, it is found that ground truth PPG data alongside original and manipulated videos enabled new direction in research on deepfake analysis and detection. In the next stage of their work, with ground truth PPG, they plan to create a new dataset with certain distribution variation as well as source variations. It is worth noting that these work looks for generator signatures in deepfakes, while the prevailing work reported by SIFTSI ETAL23 looks for signatures in real videos. For detecting signatures on both real and fake videos, a holistic system combining these two perceptives can be developed. They posed this idea for their immediate future work. In the paper 5 Digital Forensics and Analysis of Deepfake Videos by Mousa Taysir Jafar, Muhammad Ababna, Muhammad Al-Zub, Amr El-Hassan proposed a method detect deepfakes using mouth features. Nowadays deepfake videos can have an adverse effect on a society, and these videos can challenge a person's integrity. Deepfake is a video that has been constructed to make a person appear to say or do something that they never said or did. Therefore there shows the increase in demand to detect methods to identify deepfakes. In this proposed model, mouth features is used to detect deepfake video. A deepfake detection model with mouth features, DFTMF, using deep learning approach to detect deepfake videos by isolating, analyzing and verifying lip/mouth movement is designed and implemented here. Here, dataset contains the combination of fake and real videos. Some pre-processing is done prior to performing analysis. Then the mouth area is been cropped from a face. There will be fixed coordinates for face. Working on a typical image frame, facial landmark detector is used to estimate the location of 68 XY coordinates. In next step, all face containing closed mouth is excluded and face with only open mouth is been tracked having teeth with reasonable clarity. CNN is used to classify videos into fake or real based on a threshold number of fake frames based on calculating 3 variable word per sentence, speech rate, and frame rate. If the number of fake frames is greater than 50, the video is been classified as fake or else as real.